Hi, everyone. My name is Svetlana Makarova. I will be your lecturer this semester in the Algebra 1 course. The first lecture will be about set theory mainly, and I will also try to focus on reminding you most basic mathematical notation. I hope that most of you already know most of the contents of this lecture, so feel free to skip ahead or fast forward the video. Most mathematicians think of set theory as the foundation of mathematics. That is why I wanted to start exactly with this. So let me start with the basic definition. Informally, I say that a set is a collection of elements. If X is an element of a set capital X, we will write X, this symbol, in X. So for example, I can say that I can consider the set of numbers 1, 2, 3, 5, or I can write the empty set, which has no elements, or I can write a set that consists of the empty set and the set consisting of the empty set. So this set has two elements. So here is the list of some axioms and properties of sets that we're going to rely on. So Zermelo-Fraenkel axioms are usually abbreviated to ZF. And the first one says that there is exactly one set with no elements. We will call it the empty set. And the notation will be the strikeout circle. So I have already shown you this as an example. The second axiom says that two sets X and Y are equal if they have the same elements. Or I can write that X belongs to X if and only if X belongs to Y. So this symbol, I will use it a lot. It means it reads if and only if. if X is a set, then we can specify a new set called a subset of elements of X that satisfy a certain property. I will call this property phi. So I will denote this set by y, and y will be written as the set of those elements in X such that phi of X is true. So the property phi holds for X. So this form of notation is called the set builder notation. And I can give an example of how this is used. So let's consider an example of a subset. For X, we take the set of natural numbers. For the purpose of this course, we will assume that 0 is a natural number. And we can pick a subset of n consisting of those natural numbers that are even. X is even. So in this case, the property phi of X is defined to be the sentence X is even. Okay. If X and Y are sets, then there exists a set Z such that X and Y are elements of Z. So this may sound a bit counterintuitive why we would want to have such a construction, but we actually need it for the next axiom that the union of sets exists. So let me give an example. So let's say that X is the empty set and Y is the set that contains the empty set. Then we can take Z to be one of the sets from our example above, the set with two elements, which are X and Y. Of course, you can add some other elements to the set Z. Now, the following axiom says that the union over the elements of a set exists. Of a set Z exists. So this will be denoted as big union sign Z, or we can also write it as big union sign all elements of Z X. So when I don't write subscript here, it means that I take elements of the set and take their union. So let me give a couple of examples to illustrate. So the first example will be easier because it will just contain numbers. So I want to take the union of 3 sets, 1, 2, 2, 3, and 4, 5. So this set of 3 sets is a finite set, so we can write it as 2 unions. So I can take union of 1, 2 with 2, 3 with 4, 5. And the result is 1, 2, 3, 4, and 5. And notice that there were 2 elements in each of these sets. But in the resulting set, we have not 6 elements, but 5, because these 2 2s are the same. So we don't have elements with multiplicities in our sets. Okay. The second example, I want to take the union over this set Z from the previous example. So it will be the union of this and this. So the empty set has no elements. Then there is this singleton, or a set with 1 element. And if I take union of the empty set and of a set with 1 element, I get always a set with 1 element. The next axiom says that there exists an infinite set. I already implicitly used the axiom when I said that n is the set of natural numbers. In fact, natural numbers can be constructed pretty much by taking empty set many times. So the empty set would correspond to number 0. This set would correspond to number 1. This will correspond to number 2, and so on. And the statement of this axiom says that there are infinitely many of those sets, and then you can take union of those, and then you get the set of natural numbers. And the last axiom in this list is that for any set, we can take the set of all of its subsets. So for any set X, there is a set that contains every subset of X. And I denote this set by either 2 to the power X, or another standard notation is P of X. So this is called a power set. And again, let's consider some examples. So the trivial example is the empty set, which has exactly 1 subset itself. So 2 to the power 0 is 1, or in set theory, this corresponds to the set like this. And let's take some other set 1 to 3. Then 2 to the power 1 to 3 would be the set consisting of the following sets. There will always be the empty set. There will be sets 1, 2, 3. There will be each of the sets consisting of 2 elements. And finally, there will also be the set consisting of 3 elements. So the set 1 to 3 itself. And you can count that there are exactly 8 elements here. So it is 4, 7, 8. So again, you get this, that 2 to the power 3 is equal to 8. Most mathematicians also assume the axiom of choice, thus making the list ZF into ZFC, whereas ZF stands for 2 surnames of mathematicians. C stands for the word choice. So the system of axioms ZFC also has the following axiom, which goes like that. Let X be a set of sets whose members are all non-empty. Then there exists a function f from X to the union over all sets in X called a choice function, such that for all y in X, its image is contained in y. Let me first illustrate this axiom again. So an example would be, let us pick X is the set of 3 sets, 1, 2, 3, and let's say natural numbers. Then the union of X would be, so we take this union with 1, 2, 3, and union with n. And what we get is the following set. It is the set consisting of the empty set. Like it has 0, it has 1, 2, 3, and you see that we don't repeat 1, 2, 3 from there. 1, 2, 3, 4, and so on. And let us just imagine for simplicity that this 0 is different from this empty set, so they are different elements. Then a choice function would have to assign to each of these elements an element in this set. Let me call it F. So F of this set should be contained in this singleton, or in other words, in this case, we don't have any choice. It is, the image is the empty set. Now, the image of this set should be contained in 1, 2, 3, i.e., we can pick f of 1, 2, 3 equal, for example, to 2. And f of n should be contained in natural numbers. So, for example, we can pick f of n equal to 5. or it can also be equal to 2. So each of these, both of these choices would define as a good choice function. So what does this choice function says? Informally, the axiom of choice says that for any set of non-empty sets, we can pick an element from each of these sets. The statement of the axiom of choice is always true whenever we take a finite set of finite sets. So it only matters for infinite sets. Some mathematicians actually try to avoid using the axiom of choice because it is not constructible, so to say. It only states that a choice function exists, but it doesn't describe it explicitly. And this prevents them from formalizing the axiom of choice in computer language.